Hi, in this video I want to talk about inclines. When we're looking at the forces on an object that's on an incline, we use this trick. And before I go through the guts of the trick, I want to motivate why we do it. So this is Tracker, it's motion analysis software. It tracks the object and it'll produce some nice graphs for us. So you can see when Mr. Walla let go of the cart, we're getting this nice position versus time graph. And as you would expect, it's speeding up as it goes down. But this is not that great of an analysis because of our choice of axes. Right now, this axis is perfectly horizontal and vertical, and you should be imagining sort of like a grid. So on Tracker, you can actually see the grid. This thing isn't moving entirely in the horizontal direction. It is moving vertically also. So when I'm looking at the motion, I really should be looking at the X and Y motions together. And if I wanted to find the overall acceleration, I should find the horizontal component of the acceleration and the vertical component and use the Pythagorean theorem to kind of combine them. That sounds like a lot of work, and it is, unless we remember that axes are a tool, a useful tool, and we can adjust that tool to fit our needs. So what you can do is, instead of using perfectly horizontal and vertical, why not just kind of rotate your point of view a little bit? So you can kind of see that it is at an angle, and when I change the angle, I'm sort of reducing that vertical component of motion. I believe I minimize it if I set the angle to negative 4.5 degrees. And there you're getting vertical motion on the order of a millimeter. So it's really not significant. So now when I look at the X direction, according to this coordinate axis, I'm capturing the entire motion. And I haven't done anything different. I'm just really shifting my ruler to line up exactly with the motion of the cart. So that's what we do with inclines. We rotate our point of view so that if, let's say, something's accelerating, it's only accelerating in one direction. If I use the other set of, I use perfectly horizontal and vertical, there's going to be acceleration in the horizontal and vertical direction. And if you apply Newton's first law, if it's accelerating in that direction, then the forces should be unbalanced in that direction. So my free body diagram will be unbalanced in the vertical and horizontal direction when I look at the components. But if I go to this rotated axis, only accelerating down the incline in what we call the parallel direction. Therefore, the motion in the perpendicular direction, let's say this axis, there is no acceleration there. There is no motion. Therefore, the forces should be balanced along this axis. So it greatly simplifies the analysis, and we're going to go to the whiteboard to look at that further. Okay, so that was kind of the motivation for why we do the trick. I want to dive into the details. I want to clarify one thing. When we rotate our axes, we're not changing anything about the actual physical scenario. We're just changing our analysis. I also wanted to emphasize in the video that there was motion in the Y direction on Tracker, but it was like garbage. It was noise. It was to the negative 10 to the negative 3 decimal places. So that's basically just noise. And what we did by rotating the axes was make there be motion in only one direction. So now I want to dive into the details of what that looks like when we break up the forces. I'm going to start with my free body diagram. I'm going to draw it down here rather than in the center, just because it's going to make things a little bit clearer. I'm trying to do it really big. So this right here is gravity, G. There is the normal force. And let's say there is a little bit of friction. Suppose this is the cart going down the ramp that we just looked at. So it is accelerating down the ramp. So I can use this axis here to simplify my analysis. what you really want to do is essentially transpose this axis onto the force of gravity vector. You don't need to do it to friction and normal force because they act entirely, normal force entirely in the perpendicular, friction entirely in the parallel. So really what you're trying to do is impose this axis. So this axis is sort of perpendicular, and then there's this axis that's parallel. And you have to like visualize those components. So that's like something you have to just start to see. I didn't even do it that well. I didn't do that neatly. And it doesn't matter which set you use. I'm going to use this set just because that's what I'm used to. But those are the parallel and perpendicular components that you need to visualize. You have to keep in mind like the gravity, this perpendicular component of gravity is acting into the incline, and then parallel is acting down the incline. And I'm going to label this FG perpendicular, and this is FG parallel. And we can say more if we use trig. So if this is the angle of incline, this is my angle theta, I can relate it to either this angle or this angle. And you kind of should try to work it out yourself. There's many ways that you can show it. And I'm going to just try to show you geometrically. Maybe you can pause and try to show it yourself. Is this equal to this one or this one? What you can see is that if this is theta 2 and this is theta 3, that these are two complementary angles to a right triangle. So these two add to 90. And FG and FG perpendicular, these are also like forming this right triangle over here. And this is also a 90-degree angle. So I guess this is more important part. The parallel direction is at 90 degrees to the perpendicular direction. So this right here is a 90-degree angle. So theta 3 and theta 2 add up to 90, and theta 2 and theta add up to 90. And therefore, these two angles are the same. So I think when you draw the three-body diagram right there, it becomes a little bit more apparent. So I'm going to just call this theta. Okay, and now we can use trig to write this parallel and perpendicular component in terms of the hypotenuse. So FG parallel is equal to FG sine of theta, and FG perpendicular is equal to FG cosine of theta. And now that is assuming this is your angle theta. I want to say that makes sense. You can either memorize it, or you can derive it geometrically. You can also think about it intuitively if you remember your trig. So when I have an incline, right now gravity is acting straight down into the incline. And when I have it at this angle, that's when I have these components, right? Gravity is acting, some component is acting perpendicular, but then some part is acting parallel. And if you imagine how those components change as you go from 0 degrees to 90 degrees, they should match up with the sine and cosine functions. So when you're at no incline, theta is equal to 0. Which cosine function is maximum? Which trig function is maximum? Sine theta or cosine? It's cosine. So cosine of theta is maximum when theta is equal to 0, and that makes sense because gravity is entirely into the incline, into the surface. When theta is a maximum at 90 degrees, gravity is not pressing into the incline at all. So this component goes away entirely. Gravity is acting entirely parallel to the ramp. Sine of 90 is a maximum. So that's one way to remember it, or you can derive it. Another thing you can do is just sort of intuitively, you can kind of think like, oh, as the incline gets smaller, does it behave kind of like this angle or like this angle? You might need to draw it a few times or visualize it. My professor in college used to say, if two angles look the same, they probably are the same. He said they are the same, but he was joking at first. we have our components. I want to say this is useful because if you remember back to the vector addition diagram, normal force up, gravity down, and this is friction. So this little bit of room that I've saved right here, that little bit, that is your net force. And it's useful, again, these axes are useful because there's only a net force in the parallel direction. In the perpendicular direction, let me make these components clear. In the perpendicular direction, those forces should cancel out. So this right here is the perpendicular component of gravity, and that should cancel out exactly with the normal force. And we can write that algebraically. The sum of forces in the perpendicular direction is going to be the normal force minus Fg cosine theta. And I know that those cancel out because there is no acceleration in the perpendicular direction. So it should be equal to 0. And in the parallel direction, I'm getting that. And I'm saying Fn is positive because I assumed this is the positive direction and down the ramp is positive. So here I'm going to say Fg sine theta minus Ff is equal to, we didn't talk about what it's equal to yet, but this is what the sum of forces representation is going to look like when I translate this into an equation. All right, that was forces on an incline. Hope that was helpful.